Hello, everyone. This is the third lecture of the physics modules of the mini course on computation. And today we are focusing on more philosophical side. So the topic of today is called the road to reality, new insights from computation. And I would actually like to start with talking about this Penrose three words view. Yeah, and this is very related to the title of today's lecture, The Road to Reality. So in case people don't know Penrose, so Roger Penrose is a modern theoretical physicist who actually just won a Nobel Prize in physics last year. Yeah, and he has many contributions in theoretical physics, but in the meantime, he also has lots of influence in the general publics by writing lots of good books. In particular, I really enjoy one of his books called The Road to Reality. And this three words view is like mentioned in the first chapter of the book. So what do we mean by the three words views of Penrose? So Penrose was addressing the book saying, okay, so now as a curious human being, we want to understand what's going on in the physical world. Yeah, but we are the way we understand the world or trying to view the world actually is through our mind. So there's probably a mental world that is the way we try to understand things, and the mental world itself is also being constrained or as a consequences of the physical part of the physical world. Yeah, but in the meantime, the way at least for physicists probably, yeah, or philosopher, the way they try to understand the physical world, actually maybe not directly, oh sorry for the click, that not directly observing the physical world, but they maybe will have another mathematical Platonic world, yeah, trying to use this as intermediate steps to understand the physical world. Yeah, and in this mathematical words, yeah, it can be very free, but you also have to have some certain mathematical rigorosity and the structure. And we also, oh, sorry for the click again. And we also not use all the possibility of the mathematical world to understand the physical world. And we also probably cannot really understand the whole mathematical world. Yeah, but it's this is a proxy, or it's a helpful worldview for us to view the physical world. So if you look back into all the development of science or physics in particular, it's quite easy for you to put into this framework to think about. And Penrose is emphasizing the importance of probably understand each of the world if you really want to have a good understanding in the end. Yeah, and yeah, this is just a brief introduction. I encourage you to read the original passage. It's very short, maybe just few pages. It's in this book, The Road to Reality, although the whole book is 1,000 pages. Yeah, and it's slightly more mathematical involved, but I think it's very approachable. So I encourage you, if you have certain mathematical background, if you're interested in physics, take a look. And if not, but you're still interested in physics, this is another book of Penrose, which I strongly recommend. Actually, lots of the previous physics lecture are influenced by these two books. Okay, so hope this is providing you a philosophical framework to think about our future discussion, or in long run when you think about physics, math, and our own understanding. Okay, so let's go into the main topic of today. We are going to talk about the interplay between physics and computation, especially through a more philosophical discussion. And as we mentioned last time, maybe the way to discuss actually is to throw even more questions. Yeah. For example, if we want to look at the direction of how computation influences physics, we can maybe ask a very general question how fundamental does computation plays a role in physical world? Yeah, is computations also some essential elements, yeah, or fundamental elements in the physical work, particle, energy, etc. And on the other direction, we can also say about oh, how does the physical world's limits computations like can be achieved in reality, and how does those constraints actually guide us to understand computation better. So today I'll use like 4 questions in total to try to inspire some discussions between us, on these 2 broad questions. But before that, I also want to clarify a little bit, about these questions mentioned by Justin in the previous lecture about the discrete versus continuous. And the reason why I really want to mention this early, because probably people feel like, oh, the physical world seems to be very continuous. Like we use like real number or complex number to model a physical world. But Turing machine or like a computer science is inherently like a digital or like discrete. So there seems to be an immediate gap between the 2. And does this already imply like Church-Turing thesis doesn't make sense? So I have some arguments, for people to think about it, but maybe we can first watch this video. In 1901, about like the difference between digital and analog computation, in case people don't know. So we will watch maybe 30 seconds or a minute.
This ancient Greek artifact was discovered in a shipwreck off the island of Antikythera. 3D X-ray scans have revealed it contains 37 interlocking bronze gears, allowing it to model the motions of the sun and moon and predict eclipses decades in advance. Constructed around 100 or 200 BC, the Antikythera mechanism represents a sophisticated early computer, the likes of which would not be seen again for at least 1,000 years. Now, of course, this computer didn't work like modern digital computers. It works by analogy. The gears were constructed in such a way that the motions of certain dials are analogous to the motion of the sun and moon. It is an analog computer. Here is a simple analog computer for adding 2 numbers together. If you turn the black wheel some amount, and then turn this white wheel a different amount, the gray wheel shows the sum of the 2 rotations. In contrast, this is a digital mechanical computer where you can add 2 single-bit numbers. So 0 plus 0 equals 0, 0 plus 1 equals 1, and 1 plus 1 equals 2.
So I hope through this video, people have a sense of like the difference between digital and analog. And indeed both computation has been considered in a setting, and in the end of that video I showed, it also showed, oh, like a Turing machine or like digital computer, we are working on 0, 1, so it is not like a continuous variable. But in the meantime, actually other than Turing machine, and for theoretical computer scientists, they actually also study some real value computational model. And a way to think about it, it's also not so easy to formally define it, but intuitively it is like, now your Turing machine work on like real numbers. The value it can take, it can write, the state can be described by real value. So like you can still have continuous variables in your Turing machine. But it turns out that the study there, I mean, there are lots of study, but probably because not so easy to manipulate with, and also not so dramatic difference from like the normal setting. So people still focus on the digital part more. But maybe through a more philosophical argument, we can also argue that, oh, because due to our limitation of measurements to a real physical world, although it might be continuous intrinsically, but our measurements will just give a discrete result, although it's like in a very small like Planck scale. But the way we can see the physical world probably still inherently discrete. So it probably still makes sense to like focus on the discrete side. So from now on, I still stick to the discrete computation, but I think it will be good if people want to discuss continuous size in the future. Okay, so now we can start to think about the first direction from computation to physics, and the big questions we are maybe asking is that how fundamental does computation play a role in the physical world? And in the previous lecture, we have seen like a different physical theories like classical mechanics, and we view it as a optimization. And statistical mechanics, we see that, oh, through the Boltzmann's equation, we have like this kind of optimization, sampling, and counting view. And also in lots of the guest talks and the advanced section, yeah, we have seen that, oh, quantum computing also plays a very different role. Yeah, like there are different ways to implement it and different like a computation aspect within. And we also hinted a little bit the connection to like gravity and black holes. Yeah, so in short, it's like what I tried to hinted in the previous two lectures. It's like, oh, through different physics worldview on how to model the physical world, they seems to all have certain computational aspects within. Yeah, what can we say about it and how fundamental they are? Yeah, so maybe it will also be first trying to clarify a little bit when we say physical system seems to do some computation. What do we really mean, and how does it different from like the computation we talk, like either in the mathematical side or when we talk intuitively when we are like writing programs. So as Sona mentioned a little bit in her guest talk, actually the way we think about physical system doing computation is quite different from the normal way we think about like writing program or algorithm. So let's think of now suppose we have a huge physical system like a waterfall, and we want to use it to do some computation. How can we do it? Yeah, so from the physics series, actually what we do is we first encode a computational problem we have in mind, for example, some optimization problem, and we set up the waterfall in a way that, oh, the I don't know, the water, like initial water is in certain way and the landscape is in certain way, and somehow it will, the energy landscape or like the Lagrangian, yeah, if you don't know what that means, doesn't matter. It's like just it corresponding to your computational problem. So it's more like, okay, so we start with some encoding, and next we actually just let the system to evolve. Yeah, following like either Newton's law or following the the principle of stationary action, etc. We let the system evolve. And finally, we just read out, yeah, like what we observed from the waterfall. Maybe it was just determined by whether a certain sub branch of the water came out. If it came out, then it is yes, and if not, then it's no. So this is like probably when we talk about physical system compute, is usually like following these three steps. We encode the problem, the system involved, and read out. Yeah, quite different from what we think about algorithms or like computation on Turing machine. So given this kind of example of like what we see in the previous lecture about different worldviews, yeah, maybe we can consider some thought experiments. Okay, now even forget about waterfall. Maybe we can actually encode the problem into a pail of water or like a stone in some way. Yeah, and maybe even any physical system we can encode so all the computation insights. Yeah, does it is really possible? So the first questions, yeah, I want you to think about is like, okay, so maybe from like the different physical theory we see, yeah, the underlying physical laws actually is very powerful, even just for a pail of water. Does this really already say that any physical system can implement any computation? And if no, maybe it's just a small part of computation can be done. Yeah, and also maybe a further question is like, do you think computation maybe is even more fundamental? Maybe it's even independent to like the particle or like the forces, energy, etc. Yeah, and the second question would be like, okay, so given that you have some thoughts on the question of how to view computation in the physical system, what does really tell us? Yeah, and what kind of new insights can this computational view of the physical system can give us, can share that on physics? And also like this kind of computation, is it fundamentally different from like the computation we have in mind, like the intuitive mechanical procedure? Yeah, what does this really teach us? So I now will give people maybe 3-5 minutes, but please continue if you don't have time to finish it. But I encourage you to think about it and just type some thought in the chat. And yeah, I'll try to respond. And in the end, after the lecture, I'll definitely reply to every comment. So now is a good time to stop. And also feel free to speak out if you have any like a clarification questions you want to ask or some thoughts you want to talk about. So I'll pause here for 2-3 minutes. And then I'll talk about some of my view and I'll stop again for people and to read some of people's comments. Yeah. Yeah, and also maybe let me emphasize a little bit. Yeah, here there are definitely lots of ambiguity in the way I pose the questions. You can challenge it how like a realistic those things are when I say, oh, you can use a pail of water to implement any computation or certain computation, but maybe treat this as a thought experiment. Yeah, just think about like intuitively, like idealistically, if you can really set up the initial configuration like very, very precisely. Yeah, and just let it evolve with the physical laws. Yeah, like how would you say about these possibilities? So feel free to type in the chat. Any thoughts are welcome. Okay, so Kel says about the view of viewing like a computation or like as an information processing, because like information is physical and also physics objects is like kind of like carry certain information, as like Shane mentioned in his talk. So probably this give us some way of thinking about it as a information processing. Yeah, and for Catherine, yeah, from my understanding of what you are talking about, it seems that you're saying, yeah, computation is a way for a person to think about physical system. Yeah, so this probably also resonate with Penrose view, and maybe now it's like thinking of the Platonic words as like a computational word. Yeah, like computation or algorithmic thinking actually is a comfortable way for people to understand stuff. And this actually I like a lot. Actually, one reason why sometimes I still think I like a computation or like a theoretic, like the theory of computation slightly better than math. It is like I feel like the computational thinking actually is more nature for people to understand stuff. Yeah, this I totally resonate. And I see. And for Yathar, yeah, from my understanding, it's like he's saying more like, oh, we can think of physical system are like converting like energy, yeah, input to energy output. So it's like a process of like converting stuff. Yes, this is also quite making sense. Yeah, and people feel free to keep typing, but now I'll move on a little bit by giving more like a broader context for you to think about stuff, as well as posting some of my personal opinions, but feel free to keep continuing discussing through chat. So actually all the discussion or like the questions we posted in the previous slides is very, very related to these things mentioned by someone in the very first introductory class called Pancomputationalism. So the rough idea about Pancomputationalism is to think about the universe or think about the physical system as certain kind of a computing system. Yeah, but this is vague, and indeed there are different instantiation of Pancomputationalism, and now let me abbreviate it as a PC. So I'll here survey you like a three mainstream like instantiation of PC. The first one is called unlimited PC. So basically, it is very related to the previous first question about like it thinks like everything, yeah, can do every computation. Yeah, if you just properly configure the initial configuration, it can do anything. And the second view is called limited PC. It is saying that everything can do some computation. So maybe you cannot always encode any computation problem within, but everything is doing certain kind of computation, and you can view the world as this is. And the third type of PC to me is even more astonishing. It's called ontic PC. Yeah, the view is in summary, it is like thinking of the universe itself is a computing system in a sense that computation maybe is even a priori than like the existence of particle, fields, etc. Yeah. So here I want to make a warning a little bit. Yeah, people also have different interpretation of this, and this is my interpretation. And at least like there are some the most radical or the extreme worldview through ontic PC is like, oh, computation maybe is also a fundamental existence, even independent to the existence of a particle or like a field, etc. So I hope, yeah, like through introducing these three different instantiation of PC can also help you to think about like how you like answer the previous question and what you think might be more reasonable. But to move on from this, yeah, we also might ask, okay, so if I think one of them seems to be reasonable, what does this really teach us? And at least in my personal view, I think this is an issue about like a encoding problem. I feel like all this worldview, is a little bit vacuous when you are not really addressing what do you mean by like encoding a problem to a physical system. Yeah, in particular, when you say you are doing certain computation, say you use a pail of water like to solve, I don't know, so solve the graph coloring problem. Yeah, actually it is the encoding process itself is really meaningful, and it is quite non-trivial in my opinion how to do that. So I feel like if one doesn't really properly address what do you mean by like configure a computation into a system, yeah, all this view seems to be a little bit too far away from like a reality. Yeah, and also like for the unlimited PC, yeah, it also suffered lots of critics where like, oh, it seems to be the same as really vacuous, because if you say everything is doing computation, okay, if it is, then so what? Yeah, do people really provide some new physical insights? Yeah, this doesn't seem to be helpful yet for the study of physics. Yeah, so in my opinion, yeah, this could be a good start for us to clarify what's our original thoughts after we see like a physical system of different physics theory have different computational view. Yeah, but we need to dig further and be more concrete. So in my opinion, we can get inspired from the development of physics. In particular, like physicists discovered the importance of like entropy, momentum, energy, etc. Those are important physical quantities that have two important properties. First, it is kind of measurable. It is like something you really can like, I give you a physics system, you can measure it and with like good accuracy. And second, they are useful, or they are really like telling you the insights of the physical system. And so when we want to say the computational aspects of physical worlds, I feel like we also need to identify some certain measurable or like analyzable quantity or some observables. Yeah, and also in the meantime show that it is insightful, like it is really telling us something about the physical system. And it seems to me that, okay, so maybe people will use like the complexity of the computational problem or the computation done by the physical system as a physical quantity to study. But could this really be a good candidate? And in my opinion, maybe not yet, in a sense that the complexity itself now is a big problem for complexity theorists. Yeah, we don't even, complexity theorists don't really know how to analyze it, let alone physicists. So probably if we want to make this kind of connection between like computation and physics to discover some computational insights in physical system, we need to restrict ourselves a little bit more to have more constraints. Yeah, to identify what's a physically relevant computation / algorithm / inputs. And this might require some like a really good understanding on like what's relevant and what's really happening in the physical world. Okay, so I hope, yeah, through like briefly introduce Pancomputationalism and talk about some of my view can help you have some ground to keep continuing thinking about the two questions I mentioned earlier. But now maybe I'll also post for 1 minute or something, and I'll look at the chat. And I might not be able to read out all the comments, yeah, but I'll definitely reply all of them offline. But so feel free to keep typing. Yeah, and also like I really hope our discussion can be longer, but because we also quite ambitious, we want to cover more topics. So yeah, too bad we cannot. Yeah, but I also encourage people to move the discussion later on Discord. It will be fun to chat with people there too. Yeah, so I saw Justin mention in the chat, thinking of, okay, so maybe we can think of a physical system as a black box doing certain computation by like transforming input to output. So like this kind of input-output relation is like what we desire and what we think about as computation. Yes, this is also quite similar to like what maybe Yassar or Kel mentioned earlier as like information processing of like changing this, like converting input to output. Yes. And Matthew has a comment on metrics. Very cute. Okay, maybe I'll stop reading it for now, but feel free to keep continuing typing. I'll definitely check later. But maybe it's time for us to gradually move on a little bit. And I hope in the end, if we have extra time, we can go back to the discussion. So the second part of the lecture, we want to take a look at the other way. We want to see, okay, now like physical world seems to do some computation. And in the meantime, if we want to talk about computation and reality, yeah, computation still need to happen in the physical world. So what's the limitation of computation? Yeah, can the physics theory teach us? And how can the constraints of the physical world guide us to understand computation even better? So when talking about this kind of connection between reality and computation, yeah, we definitely need to mention Church-Turing thesis a little bit. And in fact, yeah, depends on what's the context you are talking about Church-Turing thesis. There are like different versions because originally it is not properly and is vaguely stated anyway. So previously, maybe especially in the previous lecture, we were talking more about the mathematical Church-Turing thesis, which means that, oh, it is stating or like postulating all computable functions. Yeah, so it's like a mathematical objects can be computed by a Turing machine. And this is roughly like what Hilbert originally asked in his decision problem and have in mind, and kind of being resolved by if you believe in this mathematical Church-Turing thesis, then Turing's uncomputable problem can refute Hilbert's theory. But if we're talking about more about the connection to reality, the physical version of Church-Turing system will then be asking, are all feasible computation, meaning that all the computation that can be done in the physical world in a sense you agree with, can also be done by a Turing machine. So this will be like a physical version of Church-Turing thesis. And you can even move on even slightly more by consider complexity within. Yeah, and this is also known as the extended Church-Turing thesis. Yeah, which say that all feasible computation in the physical world actually not only can be done by a Turing machine, but efficiently, meaning that there's not too much overhead. So you can see that from mathematical Church-Turing thesis to extended Church-Turing thesis, it's like it becomes stronger and stronger in the sense that it is very strong statements about the our belief in the physical world and the computation. And also, like if people still remember, yeah, when we talk about a little bit on quantum computation, we also says that because theoretically, people actually shows that there exists some quantum algorithm that can solve some computational problem much faster than what we believe a Turing machine can do. So it seems that quantum computation is also challenging this extended Church-Turing thesis. So the way we think about Church-Turing thesis, physical Church-Turing thesis, or extended Church-Turing thesis, and the relation to our discussion here, maybe you can think of it as a proxy for us to think about the relation between the physical reality and the intuitive and the mathematical notion of computation. So that's why, like by asking whether this is making sense, probably the first step if you want to talk about the connection between reality and computation. So in the following, I'm going to, before I post the question out, I want to give like two example as a food for thought for people to think about, how to think, what kind of questions or like we can discuss about like how the physical worlds might be a constraint for computation and guide us. So the first example is also along the line of challenging the extended Church-Turing thesis, which is about whether Turing machine can like simulate all the feasible computation in physical worlds without a lot of overhead. So as I mentioned earlier, like quantum computing is a candidate, although it's still far away being implemented. But there's actually other proposal, even not using the quantum power, even we stick to the classical mechanics, there are actually already some candidates like, maybe even Turing machine cannot simulate well. So this is an example I think introduced by some philosopher or physicist. Yeah, but it's like introduced to TCS community by Andrew Yao, who is a Turing Award winner. And this example describe a classical system and try to connect to a computational problem and ask whether this computational problem can be solved by a Turing machine efficiently or not. So just give people a flavor. Let me briefly state what this connection is. So imagine there are maybe n bodies or n particles like in the physical world. They all follow the laws of classical mechanics and in certain way. But I'll tell you the initial configuration, initial settings. And we know that after some time, actually by predicting by the classical mechanics, there could be the case where there are actually some singularity happen, meaning that maybe for one possible situation is like, two particles collide to each other, or there are certain complicated singularity can happen. But it also could be a case that there's no singularity at all. So you can think of like singularity and non-singularity. This is a discrete outcome. Yeah, a system has to be either discrete or has to be singular or non-singular after time t. So this exactly gives us a computational problem. Yeah, the input is the initial like a configuration of like this n particles position, momentum, etc. And the output is asking whether it ran into a singularity or not. So this computational problem can be easily solved by the physical world because you just run it following the classical mechanics. But is this problem solvable by Turing machine? In fact, if you can prove that Turing machine can solve it, actually then you probably also solve some important physics problem, because actually understanding the singularity of like more than 4 bodies or 3 bodies is known to be very hard in physics. Yeah, so there seems to be beneficial to both sides, either for CS people or physics people, if you look into this problem deeper. And the second food for thought I want to give you is a very seminal recent result. I'm sure some of you might already saw this on the media, but maybe doesn't really know what it really means. It is called MIP star equals to RE. So originally this paper is like 160 or almost 200 pages. It's probably impossible for people to really fully understand it. But if we just want to state the result and to think about this in a high level way, it's actually possible in 1 minute. So what's MIP star and RE? You can think of them as 2 complexity classes, where the MIP star corresponding to the following communication model, where now you have like Alice and Bob, which are our usual friends. They are, in this scenario, you think of them as like a computationally unbounded. They are very powerful. They can do any computation, any in the mathematical sense. But their kids, Charlie, is classical and is time bounded. And the goal in this communication model is like Alice and Bob want to convince Charlie about certain computational problem. So it's like Charlie receives some inputs and Alice and Bob want to give him information to convince him the result of this computation. And the reason why this is non-trivial is like because Charlie might be doubtful about his parent. Yeah, maybe Alice and Bob is not truthful. So in the analysis or like in the soundness of this computational model, we also need to guarantee that Charlie cannot be fooled by Alice and Bob. So that's why this model actually is slightly non-trivial. And now, if you allow Alice and Bob to share like quantum entanglements, and this becomes like our computational model of MIP star. And this result of MIP star equals to RE actually is exactly saying that under this computational model, under this setting, actually they can together solve the halting problem in polynomial time. So what is halting problem, if you remember? Actually, it is a problem that we saw in the very first mathematical lecture that proved to be uncomputable by Turing machine. So this theorem, although it's a mathematical theorem, is actually saying that if you have this quantum entanglement in a like this kind of a communication model, you actually can solve some uncomputable problem. So itself is a mathematical theorem, but I guess my like a food for thought question here is like, then how would you interpret this kind of results in reality in physical worlds? Because on one hand, if you believe physical Church-Turing thesis, is saying that this computational model of MIP star doesn't make sense because it solves uncomputable problem. Yeah. So now, okay, given that we probably only have 10 minutes left, let me move on to talk about the 2 questions about like the limitations of computation in the physical world. In particular, the first question in this part is asking you that, okay, we have seen like theoretically, it seems that there are lots of like algorithm, mostly like from the quantum side. Yeah, like seems to perform some like a non-trivial computation, but it's also uncertain like its relation about like really implementable in the physical or not. Yeah, how can we interpret this kind of result? I'm curious about people's thoughts, especially on the MIP star equals to RE. And the next question might be a little bit long. Yeah, but in hindsight, it is trying to ask people about like how does infinity plays a role? So while people, you can type in your response, your thoughts in the chat. let me motivate and like elaborate a little bit why I asked these infinity questions. Because this is actually very related to this MIP star equals to RE's model. Because if you notice that when I talk about the computational model, both Alice and Bob, they are actually infinite. Yeah, their computational power is infinite. And also the entanglement they share also infinite. And it is actually necessary. Yeah, in order to, show the result of MIP star can solve a halting problem, you actually really require infinite power on both sides and infinite entanglement. So it seems to be that at least in the mathematical worlds, infinite like computational powers, or like even this discussion of asymptotic care about like infinite input scaling is really, really important. But in the physical world, yeah, we also know that things are finite, although it's quite large. Yeah, so how to remedy this kind of gap between the finiteness and infiniteness? Especially, do you think restrict ourselves to, not restrict, focus on infinity really shed light on the physical reality or not? Yeah, so feel free to type your thoughts, and also, even you have thought about something maybe not exactly related to these two questions, feel free to type in the chat. I'll definitely go over later on. Yeah, but due to a time limit, maybe I'll just postpone. Post for 1 minute and take a look at the people's comment now. Okay, so maybe let me just quickly answer this question by Kel, asking why granting the all-power provers quantum communications, yeah, in the end turns out to be like helpful and important and powerful. So probably the intuition is like in this like all-power like model, actually the Alice and Bob themselves individually can already solve halting problem because they are kind of all power. So they actually can immediately solve the halting problem. But the point here is like Charlie cannot. And he also doesn't really trust his parents. So it is like given that his parents, although his parent can solve halting problem and how to use like a limited communication, but infinite entanglement, quantum entanglement, using this to convince the limited powered Charlie. Yeah, so this indeed is a bizarre setting. Yeah, but hope this makes sense and I can explain more offline. But maybe now let's move on to some of my thoughts about addressing the limitations of computation from like inspired or like guided by physics. In particular, one central idea I want to talk about here is that I think finiteness matters. And what do I mean by finiteness matters? So if you think about lots of examples, yeah, like you will encounter in the computation in real life. For example, if you care about traveling salesman's problem, you maybe care about the number of cities in the world, and roughly of the scales, like 1 million or something. And maybe you care about crypto, it's like the number of bits in a key. Yeah, so it's roughly of this order. And also like just let you know, like the number of transistors in your MacBook or your computer is roughly here, like 10 billions of this order. And the like if you care about like machine learning, deep learning, the number of images on like a typical data set is of this order, like 1 million. And also maybe if you are a mathematician, you complain about 4-color theorem. But to be honest, even in the proof of 4-color theorems, the number of cases is still around maybe 1,000. Yeah, and at this moment, people already complain about the complicatedness of the problem. So here I probably want to say, oh, the reasonable inputs you will receive, like in real life, probably just of this order. In the meantime, in biology, this is the number of neurons in your eyes, in your brains, and number of genes, number of people on Earth. But if you compare with the scale of physics, this is the number of molecules in just 1 mole. 1 mole means like one unit, like for example, in air, if you weighed it like 1 kilos, yeah, like how many molecules within. So you can see here, I want to give you a drastic difference about the scale in physical world and what we will encounter in real life. So it seems like in real life, comparing to physics, it is really finite. And physicists put things to infinity limit, probably for some good reason, because they really like tackle with a very huge scale. But for computer science or like computation, we seems to be like tackling things being really finite, yeah, of this order. So I guess I'm posing a question, or maybe we should separate the different regimes, yeah, where maybe this is the practical regimes, including biology and computation, and physical regimes where like physical system is super large, so maybe it makes sense to take to infinity in some cases. And also maybe the intellectual regimes where here maybe some of the constants in the MIP star equals to RE theorem lies in this region. And this result maybe just can be regarded as a like intellectual result, which still has its own merit. And maybe the new theory of computation I was advocating in the previous lecture should lie in this first 2 regime, while obviously, I think the current theoretical CS is more working on the 3rd regime. So I guess this is just some of my thoughts relating to the questions, and I didn't really push any like a concrete statement, and this is intended because I also want to make a discussion to be open. Yeah, so now probably is a good time for people to continuing typing some of your thoughts in the chat, and I'll monitor a little bit, and then it's almost time up, so I will conclude soon, but let me take a look at the chat. Okay, yeah, Rayo exactly asked what's the constant of the running time of the MIP star algorithm. To be honest, actually, I don't know. Maybe I was wrong. I think it probably not to like 10 to the 60, but I believe it's quite large. And let me check it out, and I can respond to people. Yeah, once I know it. Yeah, I think it was partially a joke when I say it is slicing like 10 to the 60, but it definitely is quite large. Yes. Okay. Chandra Shikhar asked, is the intellectual regime different from mathematical regime? Maybe, yeah, it could be. Yeah, I mean, I just this is just the name I gave. Yeah, you can change the name you like, and yes, you can feel free to call it mathematical regime, I guess, or Platonic regime. Maybe is a better way to resonate with Penrose worldview. Yes. Okay, so maybe, yeah, given the time, now let me give a quick summary, and then we can hear the next guest lecture afterwards. So in summary, today we try to study the connection between physics and computation on like both direction, and we try to raise more questions for people to think about this connection and what does this really teach us. And I encourage we continue a discussion. And next, tomorrow, we are going to have the final lecture for the biological lecture. Will also be very philosophical like today. And it should be fun and maybe less intense than today. Yeah, it will be maybe more approachable, I hope. And in the meantime, within less than 10 minutes, we are going to have a guest talk by Zichen on the connection between art and beauty, which is really fun. I encourage people to stay. I heard her talking about this a few times. It's amazing. And we will also have the final 3 advanced section. One on, oh, the title is wrong, but one on like like molecular computing, and by Salvador, which is actually his own research area. And also Kartikeya will talk about quantum computing from a more physics, especially condensed matter perspective. And in the end, I'll talk about black holes and its connection to computation. So yes, so this is the end of this lecture, and I thank everyone for your attention.